The recent explosion in generative AI, models capable of writing code, drafting essays, and generating video, didn't happen by accident. It traces back to a specific solution for a single bottleneck in how machines process data. Before 2017, natural language processing relied heavily on recurrent neural networks, or RNNs. These systems read text the same way humans do, strictly sequentially, word by word. But sequential processing carries a dual flaw. First, it is incredibly slow to train, since calculations must happen one after another. Second, the models suffer from memory degradation. By the time an RNN reaches the end of a long paragraph, the mathematical context of the first few words has decayed. To scale up, machines needed to move away from reading linearly. They needed an architecture that could ingest and process entire sequences of data simultaneously, in parallel. That requirement created a contradiction. If you feed a neural network an entire paragraph at the exact same moment, all the words arrive at once. The machine loses any sense of order, grammar, and narrative flow. 8 researchers at Google solved this exact problem in a 2017 paper titled "Attention is All You Need." They introduced a new architecture called the transformer. Structurally, it is divided into 2 distinct halves: an encoder on the left to process the input, and a decoder on the right to generate the output. The innovation that binds these 2 halves together is a mathematical technique called the attention mechanism. Instead of forcing a network to memorize a sequence word by word, the transformer uses attention to dynamically map the relationships between every piece of data in a set, all at the same time. Let's track a simple input sequence as it enters the model. The animal didn't cross the street because it was too tired. Before reaching the encoder, the sentence hits the embedding layer. Here, each word is mapped to a dense mathematical vector, translating the vocabulary into a geometry the machine can process. To preserve the order of the sentence during parallel processing, the model injects positional encodings. This stamps each vector with specific mathematical coordinates, allowing the machine to retain a map of the exact sequence order. Now the data enters the encoder. Here, the machine faces a core contextual challenge. When it looks at the word "it," how does it know whether it refers to the animal or the street? The encoder solves this using self-attention. This allows each word to independently evaluate its relevance to every other word in the sequence. In this case, the math weighs the word "it" heavily toward animal. Under the hood, the system executes this by projecting 3 separate vectors for every single word: a query, a key, and a value. Think of the query as what a word is looking for, and the key as what a word contains. The query vector for the word "it" checks itself against the key vectors of all other words, calculating a score to find a mathematical match. Once the math identifies a strong match with animal, the word "it" pulls the value representation of animal directly into its own vector. These bar charts show how the model runs this matching process across multiple attention heads in parallel. While one head focuses on linking entities, another simultaneously learns grammatical rules, capturing different types of relationships at once. By the time the data leaves the encoder, the output is a densely mapped context matrix. The isolated definition of every single word has been altered by its relationship to the others. That context matrix then moves to the decoder block. The decoder's specific job is to take that mapped understanding and generate a brand new output sequence, token by token. The first step in this generation process happens in the masked multi-head attention layer. The mask physically hides future words from the model during training. This forces the decoder to genuinely predict the next token based exclusively on the outputs it has already generated, preventing it from cheating by looking ahead. Next comes cross-attention, the critical mechanism where the decoder pulls data from the encoder. Here, the decoder uses its generated queries to search the encoder's keys and values. It selectively focuses on the relevant contextual memory to figure out exactly what to say next. By continuously cross-referencing its own rolling predictions with the encoder's holistic understanding of the original input, the decoder achieves highly accurate sequence generation. Following the 2017 paper, the tech industry quickly realized they could isolate the architecture's distinct halves to build highly specialized tools. Google stripped away the decoder entirely to build BERT. By relying exclusively on the encoder, They created a model optimized purely for deep language comprehension and complex search queries. Conversely, OpenAI isolated the decoder to build their GPT series. This resulted in decoder-only models focused entirely on predicting the next word, driving modern text generation. This chart shows the physical cost of this architecture. Because every token must check its relationship against every other token, self-attention scales quadratically. Expanding a model's context window requires exponentially larger data centers and immense compute power. Despite the hardware costs, the architecture eventually broke out of language processing entirely. Vision transformers apply this exact same self-attention math to small patches of pixels, treating image segments just like words in a sentence to enable multimodal AI. By successfully turning context into a calculable geometry, the transformer proved that a single mathematical concept, attention, could give machines a dynamic, holistic understanding